Hello, I'd like to begin this video by asking the question, which came first, the chicken or the egg? Well, stick around to the end of this video and I will answer that for certain. This is the chocolate philosopher, and my hope is to give another perspective to the definition of circle. We've all had conventional ideas and dedications of what we think circles are as smooth curves. But my hope in this video is to encourage abstract thinking or relearning, really, what we previously thought about circles. So, first of all, give grace to the accent, and my hope is that doesn't make things unclear as this video goes on. So we begin by digging into the background, say the motivation for this topic of discussion through the lens of a Greek mathematician, Archimedes, and I will refer to him as Archie for nickname. And then we'll talk about polygons. What are polygons? Specifically irregular and regular polygons. We'll then move on to the concept of limits and slopes. We'll briefly talk about the idea of limits and derivatives, that is, slopes. Though you may need some knowledge of calculus, but for this purpose of this video, a basic intuition is just required, not a deep, high-level math knowledge. Then we'll move on to determine expressions for the diameter and the perimeter of polygons. Afterwards, we'll use the definition of limits and derivatives and then show by stating the relationship between regular polygons and circles. Finally, we'll evaluate those limits and we'll end by talking about implications or philosophical ideas that arises from the implications from what we will discuss throughout this video. Like I said, some knowledge of calculus is good but not required, and bear with the arguments. So Archie was interested in finding the area of a circle. He noticed that a circle is too curvy. He only knows straight edges, and he came up with a simple idea. So why not inscribe straight edges, geometry inside a circle? Say geometry like triangles, squares, pentagon, and on and on and on inside the circle. Since it's trivial knowing the areas of this regular polygons, increasing the sides of this all the way to sufficiently large sided polygon, one can estimate the area of a circle. And he actually used this method to estimate what pi is, the mathematical constant pi, but never really got the full digit of it. And by this video, I hope you will be able to understand why we may never truly get to the last digit of pi. So, the idea is quite simple. Increasing the number of sides of regular polygons, you can estimate and become more like and look more of what a circle is. So in this video, instead of finding area, we're interested in finding the crucial parameters of what defines a circle, that is the circumference and the diameter. These parameters give full descriptions to circles, which we'll talk about by the end of this video. The question, why is the ratio of the circumference to its diameter equals to pi? We'll begin by answering that question. First, understanding what polygons are. Polygons are finite line segments connected to form a closed circuit. Two things characterize polygons: must be finite line segment, not infinite, and must be closed circuit, not open. So there are two general types of polygons. We have the irregular polygons and the regular polygons. The regular polygons are polygons with unequal sides and internal angles. So isosceles triangle, rectangle, and on, and whatever the bottom one is called. The regular polygons, on the other hand, have equal sides, number of sides, equal lengths of sides, and internal angles. These are called, or could be thought of as, special polygons. Examples are equilateral triangles, square, pentagon, and on. This will be a choice of geometry because of its symmetry. Now we'll talk about limits and derivatives. Like I said before, it is good to have some knowledge of calculus, but it's not required or necessary for this video for you to gain intuition. I will build my argument on this idea. You can think of limit as what happens as something approaches something. In here, it will help, this basic idea of limit will help comprehend what's really going on and why it is as such. That is why circle has a relationship with regular polygons. To give more flesh and concrete description to what limit is, I would restate it as a definition, or what defines the value of apprehension. And I'll briefly talk about what value of apprehension is for a given event function or sequence of events, and I'll talk about that too, as it approach a given value of interest, and I will show what that means as well. So this is the mathematical definition of limits in general. For those of you who are math nerds out there, will see this and will definitely know what I'm talking about. L is the value of apprehension. F of s is the given event function, and s is the value of interest. You can see as the limit as s approaches some value of interest, the event function spewed out a value of apprehension. That is a value that takes a form as it acted on by a limit. Now, consider the equation on the upper right corner. Note at f of 0, when you plug in the 0 into sine x and x, you can see that f of x is undefined. I mean, it makes sense. The 0 divided by 0 is undefined. Calculate that, and it's difficult. So for this equation, for this function, 0 is the value of apprehension. Using limit, we can see that f of x is defined at 0, and it's 1, right? It's 0, 1. So 1 is the value of apprehension. F of x, which is this function that is sine x over x, is the given event function. X is the value of interest. We will use this mathematical expression to define the circumference and the diameter of a circle. Now, this is just a basic general example to show you listeners just what I mean and what I'll be using limit as. And my hope is, as we get into using these things in determining and evaluating them on diameter and circumference of a circle, it will become more clear. A slope is really very simple. It's just a rate of change of a given function. In the graphics, you can see the tangent line that shows the slope of this function, and that's it really. It shows how a function changes. We're getting close into showing a circle is a polygon. First, we'll need to find a continuous function for our perimeter and diameter of a polygon. A general expression, you could say, that is in the function of number of sides. We'll find their slope, and then we'll evaluate their limit as the number of sides gets sufficiently large. So we'll begin with the parameter, which is quite easy. The function of a perimeter as a function of sides is given as number of sides times its length, because a regular polygon has such a distinct symmetry. It has equal sides and lengths as well as equal angles. So a given parameter could just be parameterized as the number of sides times its length, and that will give us the total perimeter of any given regular polygon. We're going to be using the equilateral triangle because it is the smallest possible regular polygon, and generalize from this shape to, say, square, pentagon, and on and on. And you can see in the picture that by analyzing this shape, we'll be able to get a fuller understanding of the expressions for the perimeter of a regular polygon, the general expressions for the regular polygon, as well as the its diameter. Now, moving on to its diameter. Observe the labeled parameters, the length L, phi, and radius sub p, which denotes the radius of a polygon. The radius is the blue line center of one vertex, and the diameter is another line from the same center to another vertex. So that gives the total diameter. One of those lines is just a radius. You can think of it like that. To relate the length to its radius, we can use the law of sines. If you don't know what the law of sines, you can Google it quickly, or find videos on YouTube that will give a really good definition and description for it. Really, it relates angle to the sides of a triangle. So using that fact, we can see the relationship between the radius of a regular polygon to its length, side length. We can simplify this equation by noting the sine pi over 2 equals 1. Rearranging, we get this equation. We'll let the polygonal diagonal be twice its radius. Then we'll have the following expression. Now we have the expression for our diameter, but we want it in terms of sides, not angle phi. So this is a problem because we want our diameters as a function of number of sides, not as a function of angle. So we'll use two facts. We'll use the fact of the total internal angle of any regular polygon, and we'll use the fact of the total internal angle inside a triangle, which is 180 degrees or just pi radians. So we'll begin by the total internal angle, the first equation. We'll see that using inductive reasoning to find the total internal angle of any regular polygon, we'll just say it's 180 degree or just pi times the number of sides minus 2. And that will denote that with a capital theta. But to find the individual measure of their internal angles, we can use their symmetry. Like I said, they all have equal internal angles and equal side length. Everything about them is quite equal. So you just divide by the total amount of sides. That is the amount of sides that each internal angle has, S. And that will give you the individual measure of the angles of the regular polygon. We'll sub that of this equation into the total total angle, the total internal angle of a regular polygon, capital theta, and that yields this equation. We use another fact that the total angle inside a triangle is 180 degrees, again, which is just pi. Observe that the two inside triangle forms an isosceles, so this implies that we can sub in our theta expression for theta and sub it into it. Next, we'll unfold the expression, we'll rearrange, cancel terms, and we'll see that our angle in terms of the number of sides of any given regular polygon is just pi divided by the number of sides. Now that we have our perimeter and diameter in terms of number of sides, we will use this definition and apply the definition of limits to continue on defining or analyzing and getting an understanding of what the circumference and the diameter of a circle is. Now we're ready to define the diameter and the circumference of what we think a circle is. Recall the definition of limits and slopes. We'll begin with the circumference because it's quite easy. This is the limit of a slope of a perimeter of a regular polygon. Note the value of interest, the event function, and the value of observation. C is the value of observation, which is the circumference. The event function is the derivative of the parameter in respect to its number of sides. That O operator is the event function, is what is being acted on. And after evaluating the slopes, you find the limit, and the limit is as the number of sides approaches infinity. That is a value of interest. So the number of sides is not just approaching some finite value. It's actually approaching infinity, an undefined value. It never really stops. What this means is the circumference is defined as the limit of an infinitely many-sided regular polygon. It's not a smooth curve. It's an infinitesimal jagged straight line. What a circumference of any circular object could look like or could be. As we see, we've previously derived the expression for our perimeter of a regular polygon. We can see the same definition. It is used for our diameter of a circle, that you can tell where the value of interest is, which is still the same, infinity. The event function, instead of a perimeter, excuse me, I keep saying parameter. A perimeter, it's the diameter of a polygon, and the value of observation is just the diameter of the circle. Now let's evaluate our limit for the perimeter of a regular polygon. After applying the definition for the circumference, which is pretty easy, this is the perimeter of a regular polygon grows linearly as the number of sides increases. It's linear. So finding the slope of a linear function is quite easy. And once we find the slope, we'll find its limit. But the slope is just L. So the limit as number of sides approaches infinity it's independent of number of sides. So we know that the circumference of of regular polygons, of infinitely many-sided regular polygons, is just the length of that regular polygon. So the circumference, you could say, of a circle is the perimeter of an infinitesimally many-sided regular polygons. Let's keep this result in the upper left corner. Now for the diameter. This is a bit arduous. It's very detailed and tasking, but we'll do the same as we've applied that definition for our perimeter. We'll do the same for the diameter. Now, because of the cosecant function, things will get messy, but I'll show you the power of limit. You see, as the number of sides of a regular polygon increases, its diameter actually doesn't grow linearly. It's as a function of a cosecant. So we need to find the slope of this function, which is non-linear, and then find its limit. Okay, note that pi and L are just numbers, they're constant. So we can apply the limit, we can break them off into the numerator and apply it for the numerator, and also apply the limit for the denominator. You can convince yourself that the limit as number size gets infinitely large, the numerator, which is just a cosine, is 1. We'll attempt the same for the denominator, but it's quite difficult. We can just apply the limit directly. We need to do some rearranging. We use u, and note as s gets very large, u gets very small. And now note that we're using u, not s anymore. So as s approaches infinity, u approaches 0. So we can just work with u instead of s. This is just a substitution variable. It doesn't really affect much what we're trying to accomplish. It's still the same thing. Now this is a famous function that has a well-known limit, which just happens to be pi squared. The pi's cancelled, but we remember with our result in our upper left corner that L is just the circumference of the circle, as we've derived that previously. So now we have the circumference of a circle is just pi times its diameter. This implies that the diameter of a circle, it is the diameter, or you can think of it as the diagonal of an infinitesimally many-sided regular polygon. Observations and implications. In our education, we're told that the ratio of the circle's circumference to its diameter is pi. But is that true? Consider this expression that relates the perimeter of a regular polygon to its diameter. For those of you who are interested in how I got this, consider this as an homework to you. Go ahead, take a stab at it. Derive this expression. Using this expression and the definition of limits that we've discussed in this video, we can show that pi arises from this definition, from this expression, excuse me. So technically, the real definition of pi in terms of regular polygons and the limits of regular polygons, as the number of sides gets infinitely large, is this expression here. And pi is a number associated with infinitely many-sided regular polygons. You can think of pi, as I would claim it, is a mathematical constant related to polygonal geometry. Objections, some of you might be thinking. You might say, hold on a second here. You're using pi and the trig function, which really stems from circle, to explain itself. Well, the trig functions come from triangles. And the pi here is not necessarily from circle. Again, it's from polygons. And it's not really only from triangles, but from ensembles of polygons. That is, triangles, squares, pentagon, and on and on. Recall the definition for phi back in this video. The pi in here is seen from two assumptions. The first one is the total internal angle of any given regular polygon. And the second is the sum of the internal angle of an isosceles triangle is 180 degree, which is a corresponding degree form of pi radians. So the angle here, the angle phi, is related and represented by pi, or 180 degrees, which doesn't have much to do with circle. The angle in a circle is from triangles, not from circles. So whenever we use sine, or whenever we see pi, it's not that it arises from circle. It arises from triangles. This is why I actually use and analyze an equilateral triangle at the beginning of this video, because it is one of the smallest polygonal shape to study, and using a more understanding of that, one could build our case. And for that I have done, and I hope I have done in this video. Still, some may disagree and say, no, you are using circular argument. How could a circle could not be a smooth curve? It can be made up of jagged lines or straight lines. Absolutely not. A circle cannot be made of straight lines. Well, not entirely true. A circle is made out of straight, jagged lines. If not jagged, but definitely straight, finite segment of line. Here is an example in a real world. This is more on a three-dimensional scale. Look out into the world. Things seems flat, don't they? Don't they? Of course they look flat, but the earth is not flat, though some of us believe the earth is not flat. But indeed, we believe and we perceive it as though that is flat, but the earth is curved, it's round. Our perception doesn't look like the earth is round. But in a more transcendent view, say you leave this world and look at it from a holistic view, one could conclude, and do rightly conclude, that the earth is round, not flat. The same argument apply on a two-dimensional analysis of what circle is. A circle is made up of straight, finite lines. And it is, in some sense, made up of infinitely many-sided polygons, making pi a mathematical concept really nothing to do with what circle is, which must I say by this time that circle is an illusion. Would that be too harsh, or am I too much in my own head? But anyway, I'll end this video by answering my question at the beginning. So which came first, the chicken or the egg? Well, I believe the egg absolutely came from. it has to be the egg absolutely came first. It's ridiculous. It's absurd that the chicken came first. My goodness, the egg absolutely came first. And for this same reason, I believe the polygons made up circles. It gives rise to a circular smooth edges when the sides are infinitely large. A transcendent geometry that uses the power of infinity. Thanks for watching. By the way, this is the chocolate philosopher. Have a nice day.